Okay, so Benjamin Hackl is going next talking about uncovering a random tree.
Thank you very much. Sorry, I can't be there in person. It's a bit of a crazy week these days. I want to talk about uncovering a random tree, which is a project that is joint work with Alois Panholzer and Stephan Wagner. And let's get right into it. So here's the process that I want to illuminate a little bit. We take a random label tree with labels 1, 2 up to n. We cover, whatever that may mean exactly, not that important, just for the visuals, I guess. We cover all vertices and edges. And then we start the process and uncover in step J the vertex labeled J. And the clue is, whenever we uncover both endpoints of an edge, the edge is uncovered as well. You can see a little animation. I hope that's fluent for people watching on Zoom and in the audience. You can see a little animation of this process on the side here. So we go through the tree and uncover step by step. And whenever we meet both endpoints of an edge, the corresponding edge is also uncovered. Why is this sort of process interesting? Well, the motivation comes from, on the one hand, studying a process that is similar to the well-known and well-studied coalescence processes. This, for example, so one that I should definitely mention in this instance is the so-called additive coalescent, which is where you have mass clusters or points with a certain mass, xi and xj, and there's a process that merges these points, these masses, with a given rate that's proportional to their mass, to the sum of their masses. And then this process is called the additive coalescent. There are many more coalescent models, most notably, apart from the additive coalescent that I've just mentioned, the Kingman coalescent, which is very, very much familiar, which is also something that is studied extensively in mathematical biology. Many other people, also many people listening in right now, watching this talk, have worked on coalescent processes and models. However, there is one aspect that we couldn't get to work on any of the already studied models, and this is the weighting of merging clusters in this uncovering vertex model is a little bit off, because you can see in the example that you have down there with the star, where the last vertex is the node in the middle, so to say, that if you uncover the vertices one by one, then for the longest time, nothing happens. You get no clusters that are merged. You just uncover step by step. And in the end, when the last vertex is uncovered, all of them get merged simultaneously. And this sort of behavior is not really, we couldn't really see a way how to model this with the existing tools. So we went on a journey and tried to see what we can say about this process. There are three questions or three topics in this context of the process that I want to speak about in this presentation. The first one that we'll talk about is the behavior of the number of uncovered edges, because that's related to the number of clusters. And whenever I say clusters, I actually do mean connected components of the tree, but clusters sounds fancier in this context a little bit. So that's the first one we want to look at. The second question is, how large actually is the root cluster? And the third one, how large is the largest cluster, so the largest connected component that we uncover over time. All right, so that's the setting basically. You can see in the background also this process sort of happening for a larger tree, but we'll get into that in more detail in a second or two. The first step to get towards the analysis of the number of uncovered edges is, in our case, we want to obtain a generating function that we can somehow use and investigate. And the function that we constructed in this case, I'll tell you what I want from the function before I actually show you how it looks, because otherwise it gets a little bit confusing. What we want is, I want to fix certain steps in this process. So I want to fix, say, J0, J1, JR up to N, some integers. And I want to have a generating function that tracks how many edges have been uncovered after J0, after J1, after J2, and so on simultaneously. So how many, this function should track all of that at once. And we can give an expression for such a function. This is it. It's actually surprisingly simple. And this function doesn't exactly do the thing I mentioned, but it does so it almost does so in the sense that the variables do not track the total number of uncovered edges, but the increments between the intervals. So we know that between step J1 and J2, the coefficient of Z2 number of edges have been uncovered, and so on and so forth. Okay, so we know that. And how do we get that? I want to say, I don't want to give all technical details, just want to give some intuition how we arrive at this sort of result. And the key ingredient is we construct a appropriate edge weight of the tree, meaning that for every edge in the tree, we assign it some weight. If we do that generically, in saying that if we have an edge from vertex I to j with I less than j, then this edge gets weight xi times yj, so two variable families, that the products of those. And then if we set it up like this, then we can use a result by Martin and Reiner or by Remmel and Williamson that essentially gives the generating function for all trees, for the weight of all trees. The weight of a tree in this case is then the product of all of its edge weights. We can give we have a formula for generating function for the trees of some fixed size n. And this is quite useful because we can adopt this strategy of assigning weights to the edges in the sense that benefits us. Because what we can do is we know that whenever an edge is uncovered, whenever the endpoint with the larger index is uncovered, meaning that the yj's play a particular role. And if we distribute if we have the interval over which we investigate this tree dissected into several sub-intervals from J0 to J1, from J1 to J2, and so on, then we actually know that as soon as the edge has to be counted, as soon as the upper end of the interval is reached. So we can set these y's to the correct variable that tracks the endpoints, these uncover interval endpoints, and in the end, what we will get is exactly the expression that you see up there, the en, which is this generating function that tracks the increments in these intervals that we have. Now with this function at hand, we can investigate the process a little bit closer. And in order to do that, we called the process KJN, the process of the number of uncovered edges after j uncovered vertices. So j runs from 1 to n, is sort of the time step in this process. And what we can observe is we can make a rather simple argument for the expected value of these uncovered edges, actually, because we know that as soon as we have j uncovered vertices, j choose 2 out of the n choose 2 possible edge positions have been opened up and uncovered. And as we are investigating all labeled trees, we know that across all of them, every position for an edge is equally likely, which means that there are, as we have n-1 edges in total, we can immediately derive the expected number of uncovered edges after j uncovered vertices, which is given as j times j-1 over n. And this is useful, but we want to learn more about this process. And the way how we do this is we we want to see whether we can describe the limiting behavior a little bit more. For technical reasons, we switch to from this discrete time process to a linearly interpolated continuous process scaled on the interval 0, 1. So the role of t here is actually now j over n in a sense. And what we want to look at is the deviation. What happens if we look at this thing, if we look at this process, subtract the mean, and then how does the deviation from the mean look like? And we can visualize this. So here's the process on an actual tree. If the thing starts running, that would be even better. There we go. So we uncover the tree. On the top diagram, you see the number of, on the top diagram, you can see how the number of edges develops. The bottom one is not that important. It shows the this equivalent number that I mentioned in the beginning, the number of connected components in the tree. So you can see this develops up and up. We subtract the mean. So the mean is actually in green, which is a bad choice, as I realize now. It can't be seen that well, but still, the curve fits pretty well. We subtract it. And what remains is this thing here after rescaling. And that doesn't look so bad. So the question is, does this particular curve that we see here, can we characterize this somehow? And one good guess that one can make in such a situation is, well, I have some sort of stochastic process. I have subtracted the mean. Perhaps the thing that remains is sort of a Brownian motion. And in fact, in this case, it will not directly be a Brownian motion, because we know that from the construction of this expected earlier and subtracting a mean, we know that the endpoints will be fixed on the axis. But that could mean it could be exactly that, the Brownian motion, where we condition on the endpoints, so to say, being fixed on the axis, so Brownian bridge. However, it's also not that, as we'll see in a moment, but it's close. It's very close. I'll show you the result. So we take the process, we center it, we rescale it appropriately with a factor of square root of n. And this process we can show converges weakly to a limiting process, set infinity, which is defined as 1 minus t times Brownian motion with argument t squared over 1 minus t. So W of t is the standard Wiener process, the standard Brownian motion. And this is somehow curious, because if you look at how you can define a Brownian bridge, the process where you take a Brownian motion and then condition on the endpoints being on the axis, you can actually see that this is pretty close, in the sense that for the Brownian bridge, you have this expression here, 1 minus t over the Wiener process with argument t over 1 minus t. And for our limiting process, this is almost the same, but with a t squared here in the numerator of the argument of the Wiener process, which is nice. Some words on how we can get this. There are two ingredients. So we go the route where we show that the process is sufficiently tight. We have tightness, meaning that there's a uniform bound over n that shows that if the process cannot exceed a certain bound, or will not exceed a certain bound with high probability. So we have this on the one hand, and how you show that is you can actually construct from the discrete version of the process, you can construct the corresponding martingale and then use Dup's LP inequality to arrive after some steps at this inequality here, which bounds the probability. And on the other hand, we need the convergence of the finite dimensional distributions. So if we take a vector of these, and this is why we constructed this generating function in the beginning, where we tracked the progress of the edge uncover steps in various positions simultaneously. if we take this random vector, we can show with this generating function that we had before, if we turn it into a probability generating function, then actually you can see that this expression here can be interpreted as the sum of multinomial variables, so the probability generating function of the sum of several independent multinomial variables. And then we can use essentially, I'm skipping some technical stuff obviously, but we can use the multivariate central limit theorem to arrive that at the conclusion that the variables that track the increments between these measurement points, that these are asymptotically normally distributed. And then with a simple transformation, the same holds for the original, this vector that actually tracks the number of uncovered variables, uncovered edges. All right, so that's for the number of uncovered edges. So we can show there's a nice limiting process. So we have the mean and we have the behavior of the deviation basically. Let's switch gears and look at the second problem that I mentioned, from counting the number of edges to counting the size of the root cluster, which is basically the connected component the root of the tree is located in. And to do that, let's play around with some combinatorial classes. We have a class T, which is just rooted labeled trees. We have a class G, which is a refinement of the trees, where uncovered vertices are marked with a variable u. And then we have a second refinement of T, where the uncovered vertices in the root cluster are additionally marked with v. So basically, we have a combinatorial class, all rooted labeled trees, and the variables, the vertices that are uncovered are marked with u, and the vertices that are in the root cluster and uncovered are additionally marked with v. All right. From this description, we can set up symbolic equations for these combinatorial classes. On the one hand, the equation for f is simply we have either the root is uncovered, then it's just z to account for the size, and the bunch of trees attached, their vertices might be uncovered or covered, doesn't matter. Or the root is actually uncovered, then we get z for the size times both u and times a factor of both u and v, with a bunch of children attached again, in order to symbolize that any children of the root, if the root is uncovered, any children of the root that are uncovered will also be part of the root cluster. And the second part, if we have G's and the refinement where we just care about covered or uncovered, there the root is either covered or uncovered, which gives us either just z or z times u, and a bunch of children attached to the trees again. Right. So that gives us the symbolic description, and from there, the purple book or whatever tells us how we can derive symbolic functional equations for the generating or the corresponding generating functions from that, for the exponential generating functions. The right one, G, is almost is almost a tree function, and with knowledge of G, we can also say some things about F. And one thing that we can say pretty soon after doing the usual things, taking partial derivatives, plugging the right values in, we arrive at this equation here, namely the expected the expected size of the root cluster after uncovering k of the n vertices is given by this sum here, where we have in the numerator j times the k falling factorial j, and in the denominator n to the j. And the question is, well, how does this thing behave actually? I should have shown you maybe a picture already before, but how does the root cluster actually behave? Here's an example in one image that shows how the root cluster grows overall. For the longest time, nothing actually happens. The root cluster stays very, very small, and only in the end, very rapidly, the size grows significantly. And this is something that we that also that looks similar for all sorts of trees, or for random trees. This is I think I plotted this for a tree of size 2000 or something like that. Will always look very similar to that. For the analysis, we can actually give a pretty precise description how this expected root cluster size behaves. Here it is. Depending on where we are with k as a function of n, depending on how many vertices we have uncovered, the behavior, the size of the root cluster will be different. As long as k is in little o of n, the size of the root cluster is k over n, very small. As long as the size of the root cluster is linear, so as long as soon as we have uncovered linearly many vertices in the tree, the size of the root cluster is a constant, as long as alpha is less than 1 at least. As soon as we have uncovered, as more than root n many vertices are still covered, in that case there are n squared over d squared, where d is the difference, the number of still covered vertices for the root cluster. Then finally we find that the root cluster has linear size as soon as we are in the critical region, where we are only about root n vertices away from uncovering everything. And then finally, if there are less than root n vertices still covered, then the size of the cluster is n minus constant times root n. And that's the behavior of this. How can we say this in such a precise way? Well, there's a very nice integral representation of the sum above, namely this one here. Could make a screenshot and check that this is actually true. It's not hard to check that this holds. And the integral representation is very helpful in terms of finding the asymptotic behavior of the sum in these different regions. All right. What we can say for the expected root cluster size, actually, we can pretty much replicate this in terms of the distribution of the size, because we can extract the probabilities that the root cluster has certain size and describe these probabilities also very precisely. For that, we can either use Lagrange inversion on the generating function f that we constructed above, or we can use a very nice combinatorial result on counting forests that look a particular way. If we do that, then we can find explicit formulas for the generating function for the probabilities of these root cluster sizes. We don't have to talk about that in detail right now, because it's more interesting to say what happens not through distribution. Again, we have our different regions, and in these regions, the distribution of the root cluster size will converge or do something well, according to the location. We either have, as long as we are in little o of n, then the root cluster size converges to the degenerates. So this is a discrete. It just degenerates. In case we have linearly many uncovered vertices, we have a non-degenerate discrete random variable. That's the limit. If it's subcritical, so more than root n uncovered vertices, then the rescaled cluster size converges to a gamma distribution. If we have in the critical region, it converges after rescaling by n to a continuous random variable, depending on the constant c of the order of magnitude. And finally, in the supercritical case, again, after rescaling, we again have a continuous limiting distribution for all of this, for the root cluster size. I'll skip this slide. I'll skip this slide and end with some remarks on the characterization of the behavior of the largest cluster. Basically, we can take these results that we have found for the root cluster and carry over some of them to analyze the largest cluster, because at a certain, so for one part, at a certain point, the largest cluster will be the root cluster. At the very latest, as soon as the root cluster has more than half of the vertices, then there cannot be a second similar a second cluster that's similarly large. And this sort of argument can be tweaked to actually show that in this case, I'm doing them in the wrong order, sorry. In this case, there's with high probability a giant component of size, of linear size. In the other two cases, in the subcritical case, so as long as we are more than root n vertices away from uncovering everything, as long as more than root n vertices are still covered, the distribution normalized by n degenerates and goes to 0 in probability. And finally, in the critical case, which is quite interesting, again, the rescaled size of the root of the largest cluster converges weakly to a continuous limiting distribution, and that's a sort of curious behavior again in this critical region. Let me briefly sum up what we've done with this uncovering process. So we have the number of uncovered edges. We have a process. We have characterized this fairly well. And we have also characterized the distribution of the root cluster size for the case of rooted labeled trees. For the size of the largest cluster, we also have some results, in particular around this critical region where at most where we are around root n vertices away from uncovering everything. And finally, on the way, we've met neat combinatorial results. One I've mentioned with the enumeration of the special forests, and the other one I've skipped because, well, I'm talking too slow apparently. Thank you very much.
Thank you, Benjamin. Questions for Benjamin?
Hi, Mark. Can I ask a question by Zoom?
Absolutely. Hi, Jim, Phil.
Hello, Benjamin. Thank you for a very interesting talk. I enjoyed that, and it was technically very excellent too. Something I missed is this: what is the motivation for studying this uncovering process?
Basically, because it's fairly familiar or fairly similar to the usual
the coalescent
processes. And it's so intriguing that you, on the one hand, if you work with the edges and say you add one edge at a time, that you can that you can characterize all of this very, very simply. And on the other hand, if you say you uncover one vertex at a time, that everything becomes more complicated in a sense. So that was sort of intriguing.
Yeah, but I mean, but what brought this problem up in the first place? I mean, what you just, I know you like me and others look at trees all the time, and it was just like, well, did you just dream this problem out of the air, or did someone come to you and say, what would happen if, you know, we do this, or how did it come up?
I'm not sure. So for the exact background, you probably have to ask Stephan or Alois Panholzer. I remember Stephan telling me that they discussed this on a train ride at some point, but I'm not sure. Maybe Stephan knows more.
Okay, thank you.
You want to comment on it, Stephan?
Well, it's not that we bring exam papers and entering grades on the list
Grading exam papers?
Yes, exactly. So I have a file of exam papers in particularly random order and have an output with nice list. So entering grades and all this grading the papers. And only this is
Stephan said he's entering grades as he graded papers.
so I was wondering, so what happens if you do this not just on the bigger list, but also on the trees?
And what happens if you do it in a tree instead of a list?
And then I discussed it with Alois and okay, several years ago. Maybe discussed it together at some point. But nothing happened. So it's.
And it just grew organically from discussions with Alois.
Complicated story. But in some other ways, also very simple.
I think Conrado's got a question. Let's see. Conrado's raised his hand.
Yeah. My question, well, rather than a question, maybe it's a comment. One of the motivations for such kind of analysis could be related to studying the union find data structures. So when you reveal a node, is like adding an element to the partition, and when you do a union, you are connecting, you are revealing an edge, you are connecting to two classes. Benjamin, do you think that this model could be relevant to analyze union find data structures?
I mean, I'd have to look at it in more detail, but it sounds very, very promising because
Yeah.
it's essentially what you have. You uncover these connections step by step.
Yeah. Thank you.
Okay, other questions for Benjamin?
Okay, may I ask a question?
Yeah, absolutely, Stephan.
Yes, so, okay, Benjamin, so this was very nice and interesting. I have, well, first of all, I have a short comment to Stephan's answer about grading exam papers. That reminds me that I once wrote a paper about a different problem. It was not connected to trees, but that also came from at least a story I heard of a way another professor did to sort exam papers after having graded them. And there came out some Brownian motions like limits in that case too. So grading papers may be very productive for research. But my real question is that there seems to me to be some similarities and maybe relations with the problem of percolation on the graph, because here you uncover, but if you do it from the opposite direction, you instead start covering verses at random, it looks like some kind of percolation process. Have you explored that, and whether there are any useful connections?
There is. So if you look at this classical tree percolation process, if you turn that around, I think Jim Pittman has some work on that in, and the thing is then called a tree coalescent. Mm-hmm. And this has the same problem essentially. So it behaves similarly and cannot capture this. You uncover many things at once, or you uncover nothing in one step. That I'm not sure whether we can perhaps explore this a little more if we turn the process around and say, no, we do percolation on vertices or something like that.
Yes, yeah. So Pittman's process is percolation on edges. I think where you said yes. So this is some kind of vertex equivalent there. Okay, thank you.
We're looking for a keynote next year on how to grade our papers. Other questions for Benjamin? Okay, yeah, Michael Domona's got a question.
But you can also invert the process, so not.
Yeah, what if you invert the process?
But
not one after the other, but delete it. Starting with the full tree.
Reminds me a bit of cutting off some parts of this is a
yeah, cutting off parts of the tree.
Where you cut off part of the tree and then you are asking when are you just select just getting the root cutting of edges. So this is cutting off vertices. But is there some relation to this process, or did you find some relation to this deleting process?
Mark, can you repeat the last part of the question? Did we find some process that's related to the deleting equivalent of
Yes,
of the deleting part.
yeah. Did you find some relation to this deletion process, or is this maybe another potential motivation for studying this process?
I think it. I don't think that there's a direct connection, but it could very well be more motivation to well, either motivate why we studied this particular problem, or even going beyond that.
Benjamin, thanks so much for inspiring so much good discussion. We enjoyed your talk. Thank you.
Thank you very much.
Yeah.